everybody, my name is Michael Walker. We'll be talking about the same thing Landon just talked about. I'm the reporter for Group 2, and we did the ice water bath experiment. So a little bit about this. This was supposed to be an introductory experiment, just to introduce everybody in the class to the process and what the lab is going to be like, and safety rules for the lab. But it's also to better understand the properties of thermocouples and how exactly they work. And yeah. So objective and procedure. We had to record the transient response of a 1/8 inch type K thermocouple and experimentally determine the time constant of it through data manipulation. And for the ice water bath, we began recording temperature at room temperature, and then we inserted into the ice water until it reached equilibrium, and then we removed it from the ice water and allowed it to warm back up to room temperature. So for the apparatus, see, we had the thermocouple, ice water. This was our relay for the data, and then we had this program with a thermometer to record the data. So this was our raw data. Similar to what Landon said, we had some issues here, which this is inserted into the ice water. It began pretty well, but then it kind of flatlined right around 3.5 or 4 degrees Celsius, and then it dipped again. And I think when it dipped is the lab instructor actually walked over and told us to try starting it around, which that did get us down to 2 degrees. And then after that, once we removed it, we began the warm-up process. So this was into the water. Again, as you can see, we had this long period where it just kind of flatlined and stayed the same. So the first thing I did with this was actually normalized it using the T functions, or it's like, I can't remember exactly what's top of my head, but using normalization, it made our range go from 1 to 0 instead of, all the way up to 22 degrees Celsius. And then from there, did the log of the normalized, and actually did my seconds on the y-axis and log on the bottom. So that way I wouldn't have to do the inverse and all that stuff. And it would give you the time constant and as this. But the problem is the R squared value on that data was way off. So the closer your R squared value is to 1, the more accurate your linear representation is. So it only being 0.34, it's bad data, basically. So to adjust that, I took away the portion where it had flatlined, and that gave us a much better reading, and it brought it up to 0.89. So it's still not great, but it's more acceptable, and that gave us a slope of 2.35, which is pretty close to Landon's 2.4, I believe. And then for out of the water, again, this is just our raw data coming out of the water, and it did go a lot smoother. And then after normalizing it again, you get the range from 1 to 0. And then using the natural log function on the normalized data, you get a nice slope. And this, as you can see, this is much better representation of the data with the R squared value of 0.98 and a slope of 121. So basically for our results from hot to cold, I found an initial thermal time constant of 17.2, but after adjusting it, I got a 2.35.